Hello everyone, and welcome to this week's Scrum seminar. So, barring this is a holiday, but we have an alternative, as Professor Kanidakis says, to attend the seminar. And this week we have two talks, both from Europe. The first talk is a joint talk by Dr. Michael Kraus and Rafael Bischof. And before he begins, I'll quickly introduce both of them to all of you. So Dr. Michael Kraus is a senior researcher at the chair of concrete construction and bridge engineering and the co-director of Immersive Design Lab at the Design++ initiative at ETH Zurich. He teaches courses in the area of scientific machine learning for the built environment in graduate and undergraduate civil engineering curriculum. His research includes the development of deep learning methods and their application with a special focus on structural design issues as well as component verification. His student, Rafael Bischof, has completed his master's degree in computer science at ETH in 2021. Within his master's thesis, he studied the application of pins to several differential equations arising in civil engineering. One of the findings of his thesis eventually led to the development and publication of a novel loss balancing method, acronymed as RELO-BRALO. Rafael currently works as a research assistant at the Institute of Structural Engineering at ETH Zurich on further development of pins as an alternative, establishing numerical techniques such as finite element method. So please join me in welcoming the speakers, and you may want to begin. Dr. Michael.
Yes, sure, thanks. I hope you can see the screen now.
Yes.
Cool. Yeah, thank you, Samdata, for the introduction, and thank you, Professor Kanidakis, for the invitation. It's really an honor to speak here, and Rafael and me have read a lot of your papers and work, and were inspired by that actually to get involved in that stuff. And I divided the talk a bit into two parts. So at first, I would like to give a little introduction, like really very short, to what is Design Plus and why we are concerned from the civil engineering community with AI at all and pins in specifics. And the other thing is that this leads to the motivation why we got in touch with Physics for Deep Learning. We would like to give a little introduction to the state of the art, and then the development of, we call it RELO-BRALO, but maybe that's a very German pronunciation. Then we would like to present our findings of the numerical experiments on three PDEs, and finally wrap up with some conclusions, and that I think enables us to give and start discussion. So as I said, a really short background on what is Design Plus. That's a new research center at ETH in the departments of architecture, civil engineering, and computer sciences. And we try to address the pressing sustainability challenges which we face meanwhile. And we want to do that in a way that we advance systematic construction productivity and achieving the high quality in the built environment. We do that by a combination of rational and intuitive decision-making processes during design and planning of structures using computational analysis, especially artificial intelligence and extended reality. And our core design activities include this interdisciplinary research, teaching, and knowledge transfer with industry, but also amongst our networks at ETH and beyond that. Very short background on that. So engineering design usually happens at a computer. Information then is transferred to the building site because we need to build then in the end some structures. And along that process, we gather information about mechanical milling of different parts of that structures and the construction process itself. All that data then is transferred back to the design process, and this is the core idea of Design++, to establish AI-based methods on the forward and the backward process during the phases. The team of Design++ consists of an advisory board. Maybe you know some of those people, a steering committee and senior researchers. I'm part of the senior researcher team, conducting some research projects and having constant interchange with the professors from the steering committees and the advisory board. And yeah, let's get a bit to the motivation why we come into touch with pins. So if you look at a graph where we would plot on the x-axis a timeline, and setting up a building and the planning for that would be delivered in some phases. So in the beginning, there is a strategic planning where the engineer and architect would sit down with the building owner, and they would decide on very early sketches of how this building or structure could look like. And then there would be a preliminary planning phase where rough calculations would be done. And first after that, then a stakeholder would decide, I want to build that structure. And then the really project planning would take off. Finally, we would construct that thing. So if we now put down the design freedom, meaning how much I can change over time, and plot a line for the costs associated to those design changes, we would see the following. I think that's more or less clear. The later in a project stage, the less I can change. And if I change something, that's very costly. So current methods for doing that would be associated with the most efforts taken after the stakeholder takes its decision to realize that project, and then really architects and engineers would go into detail and plan a lot of things. That is a bit in a contradiction that key decisions on budget things or sustainability, constructability, and so forth, those key decisions are really taken in very early stages where a lot of analysis did not yet happen. And that's the problem why you would see today a lot of what's called prototype buildings, all more or less suboptimal in the sense of not really maturely designed. And that's because, as I said, key decisions are taken at early stages where a lot of analysis is not yet done. The idea now is if we have all the data from other building projects, we could use AI in different applications and use that knowledge which we gather from historic buildings or computational analysis of those projects to accelerate the process, but deliver some information at earlier stages so that there is really an optimization possible. And the vision now is to use that as a computational backend to really achieve eco-friendly aesthetics and powerful buildings in the future. Associated with that, I think two things have to be mentioned. The one is the physics-based modeling, which is very natural in the engineering disciplines. We would use some physics to describe the system, and then some numerical methods like finite elements to do that. I think digital twinning now is kind of a buzzword in that respect. To some extent, engineering was always doing kind of digital twinning because our analysis would have taken place before building. The new thing, I think, is more really having data over the whole life cycle, especially from structural elements or infrastructure like bridges. And if you look at the hype cycle, I was really happy to see that the physics-informed AI is now also on the hype cycle, because that is really a thing where we were motivated to look into that. And really to give you a last motivation for that. So in the civil engineering domain, usually if you draw this graph about availability of data and availability of physics, what traditionally engineers would have done in the design and analysis phase, there is little data about that structure, but we would use a lot of physics, mechanics, and all the things to come up with prediction of the performance of that structure. The other thing, what is heavily done today in engineering, is structural health monitoring. There is a lot of data, and maybe people are not using physics a lot. And then, the machine learning community, on the other hand, provides methods. Here, the pins, and then the depot nets. And as I said, we are focusing at the moment in our research center on that. faith of a building. And therefore, for us, it was natural to look at pins as a computational backend to do our analysis. And as I said, that was the motivation for, really getting into touch with physics-informed learning. And this led a bit to really diving into some of the obstacles which can be found. And to that end, we would like to continue now to present to you what is behind Relo and what we found about it. And with that, I would hand over to my fellow presenter, Rafael, and ask him to continue.
Michael, can I ask you a question on more like on the design side? Yeah,
sure.
So in, I know in mechanical engineering, there is this notion or a new paradigm of what is called set-based design. You ever heard of that?
Not really, no.
So set-based design was started, I think, 2016 by Toyota. And instead of trying to find the optimum, at least in the early stages of the design, they try to find islands of infeasibility in the parameter, not feasibility, but infeasibility, and eliminate those. And therefore you stay with islands of feasibility in the parametric space. And so that's like, that allows them to do, at least in the early stages, to do sort of parallel work. And now, for example, the US Navy has adopted this, and many Chevrolet and so on. But it was introduced by Toyota in 2016, I think, under the name set-based design, that this idea of parallel efforts in the early stages, because you're not trying to find an optimum in a multidisciplinary design. And here now, the buildings with this eco-friendliness become more complex, right? So I was wondering if that has found its way, but maybe not yet.
Not yet, but very good. I took it down, and maybe I come back to you. So there is some other work which has been done recently. We used some conditioned autoencoder or conditioned GANs, but that is another story. We can also talk a bit about that. But thanks for the feedback. I've not heard about it, but I think it's not really known in civil so far.
Yeah, probably not in civil. Yeah.
Thanks.
Sure.
Okay. Rafael. So I would take or give the stage to you.
Yeah, thanks also from my side. It's a great honor to get this opportunity. Just as we gave a short introduction to physics-informed neural networks because, of course, they were developed at your group, but maybe not everyone is familiar with them. Just as a test, can I change the slides? Do I have control? Yeah,
yes,
okay, perfect. Thanks. So physics-informed neural networks are classical feed-forward neural networks or any other architecture that you'd like to use. They have inputs and an output, but instead of stopping here, we use automatic differentiation for calculating various higher order derivatives to then build a partial differential equation, a loss function that includes partial differential equations. So we can include the governing equation, boundary conditions, initial conditions, and if we have it, we can also include data and then combine it into a loss function and optimize through gradient descent in the hopes that the network will converge to the right solution, the unknown underlying function. Some extensions, state-of-the-art extensions that were developed in the last years, they can be coarsely grouped into four topics. One is the architecture search of pins, so which architecture favors the performance of pins. There's, for example, the multiplicative residual connections that were developed by Wang and others, and attention mechanisms more recently. So there's some inspiration from other fields, from classical neural networks, mainly, of course, that people found to work also for physics-informed neural networks. Then there's something more proper to physics-informed neural networks, where the physical domain is decomposed into multiple parts to solve, and different pins are used to solve these parts in the hopes of facilitating or making the problem easier and also parallelizing the computation for speeding up the training. Then, of course, big topic is also the initialization with, again, ideas coming from classical neural networks with transfer learning and meta learning, where you try to train networks on different tasks and hope that these trained networks are then close to the optimal networks for another unseen task. And the final topic that is the most important for our work now is the loss balancing. And here we also took inspiration from other fields of machine learning, mainly computer vision. So that grad norm and soft adapt were proposed in computer vision. If you think about autonomous cars, they have to estimate the depth in an image, they have to classify objects, they have to find lines and so on. So multi-objective optimization is also very important in computer vision, and then learning rate annealing proposed in the context of physics-informed neural networks. So we will look at these methods a bit more closely to motivate then our proposed policy. Maybe as a motivation, why is loss balancing even necessary? The training of pins, as I said, is a multi-objective optimization where we have, for example, we have always the governing equation and then some boundary conditions, some initial conditions, and so on. And the standard approach for turning this into a function that can be optimized through gradient descent is through weighted linear scalarization. So we sum up all the objectives and weight them with some positive real value. Why is the weighting necessary? There are a few reasons. One is that there might be differences in complexity between the objectives, right? If the network is centered around 0 and initialized around 0, then a boundary condition that has to go towards 0 will have an easier time than a boundary condition that has to go towards some other function. Then there are differences in magnitudes between terms. We're bound to physics, right? So that means that we're also bound to different units of measurements. So we might have one term in seconds, another in meters, another one in Newton meters. And these differ in terms. And what that means in gradient descent is that some terms have a bigger magnitude than others. And if we don't scale, if we just take the sum, then we end up following the most prominent term while ignoring the other ones. And what that means in physics-informed neural networks most of the time is that the governing equation has the biggest magnitude. And so we end up ignoring the boundary conditions. And as you may know, then there exist a lot of solutions, valid solutions that satisfy the governing equation. But if we don't respect the boundary conditions, then it's not a valid solution, or not the one that we're looking for. And finally, there are also differences in modeling capabilities of the network. So keep in mind that we're fitting terms in higher orders of differentiation, and also the activation functions have different shapes in these higher order derivatives. And maybe a term that is fitted in the first derivative has a shape of activation function that is suboptimal for modeling the problem at hand. And so the network might have more problems fitting the first derivative than it does the second derivative, for example. And we want to find some way of balancing these terms. We can do it by hand. So these lambdas can be chosen by hand, but that's very laborious. And maybe we'd like to let this evolve over time. So maybe we want an aggressive balancing at the start of training, and then once the network has found the momentum, let it reduce the scaling. And we want to find a policy for that. And existing methods is, for example, learning rate annealing, where we select scalings based on gradient statistics and apply exponential decay for remembering past statistics. And more specifically, how this is done is we take the gradient of the governing equation, gradient of the loss of the governing equation, the absolute value, and the maximum value of this term, and divide it by the mean value in the losses or in the gradients of the boundary conditions. Now you see that if the signal for the governing equation is very high while the boundary conditions are neglected a bit, then the scaling for this boundary condition will account for that discrepancy and counter it. And then there's this term for exponential decay, where if alpha is very high, then we put a lot of emphasis on past statistics, while if alpha is low, then we increase in stochasticity, but also the flexibility of the network of adapting more quickly to changes. And then we optimize through a gradient descent classically. One downside is that it requires separate backward passes for each term. So that might be computationally expensive. Also, the second method that we looked at was grad norm. The authors take a different approach here by making the lambdas trainable and update it through gradient descent and a separate optimizer. So this loss function here is for optimizing the scalings, not the parameters of the network. And what they say is they want the norm of the scaled gradient to be equal to the average norm of the gradients multiplied by some value. And this value, they choose it in this way, which is interesting from a physical point of view. They take the inverse rate of improvement of the network since the beginning of training. So they take the loss function at time step 0, and they divide the current loss by this value. So this gives the progress of the network so far, and they normalize it. So what this does is it weakly enforces Pareto optimality, right? Because if one term improved a lot while others improved less, then the rate, these rates here will counter or will give more weight to the terms that have improved less so far. And this is physically a good property to have. But it's also computationally expensive and very difficult to tune, because we now have two different optimization objectives, something that we wanted to avoid in the first place, actually. So as a last method that we looked at was soft adapt. It also keeps track of relative improvement, but it uses only loss statistics to do so. So they relax it by taking the current loss and dividing it by the loss in the previous time step, and then take the soft max of that. What this does is it still reinforces Pareto optimality, of course, in a very relaxed way, while being significantly more efficient than grad norm. But it forgets statistics from past time steps. But this can be a good or a bad property, depending on the problem at hand. Finally, our proposed policy, we call it relative loss balancing with random lookbacks, so ReLO. It also keeps track of relative improvements. It utilizes only loss statistics and remembers past. So this one, utilizing loss statistics, this is borrowed from soft adapt. Then remembering past statistics through exponential decay. This is borrowed from learning rate annealing. And finally, introducing occasional lookbacks. So we call it SODAT. To start off training, this is borrowed from grad norm. So the main function is down here. Let's break it up for readability. If we have a very low value for alpha, then this term here falls away. And we take the lambda hat of t and the previous time step. And what we end up with is soft adapt, basically, because we have here the loss of the current time step divided by the loss of the previous time step. And we just chose to multiply it by the number of terms here, because if all the terms improve at the same rate, then we want the scalings to be 1, so no changes. And if alpha is not 0, then we also have this part where we have a Bernoulli random variable here with some probability of being 1 and some probability of being 0. And if rho is 1, then we end up with a classical exponential decay. So we take like learning rate annealing, we take the previous lambdas and add the current scalings to it. And if rho is 0, then we look back to the beginning of training. So we take the lambda hat of the current time step with respect to the loss at the beginning of training. And what this does is it it occasionally reminds the network of the progress it made since the beginning of training. And so we can choose here a lower alpha because we don't need to remember the statistic for so long because we're reminded from time to time. So this gives more flexibility. And furthermore, it gives occasional impulses to the network. So, and these impulses have shown to help the network escape local minimas. So this method also weakly enforces Pareto optimality and requires only one backward pass. We conducted experiments on 3 different differential equations, Berger's equation and Helmholtz equation. These are very well-known equations. The Kirchhoff plate bending equation maybe a bit less, but since we were interested in structural engineering problems, this is a very prominent one. And we looked at the forward as well as the inverse problem for each one. Before I go into that, I want, however, to say, lose a few words on the hyperparameter tuning. So we just defined ranges for the major hyperparameters and then used Bayesian optimization to get a coarse estimation of which could be the best parameters for each, or best values for each parameter. And then I used grid search for fine tuning. And this worked fairly well for getting an initial estimation for each parameter. So Berger's equation, as I said, very well known. It's a shock function. I'm, as computer scientists, not in a good place to explain it to you, but as I said, it's well known, and it's a first order differential equation where we also add this diffusion term in order to make the shock a bit smoother. And this is important for our network because neural networks are very bad at modeling discrete jumps. And so this helps us approximate the right solution a bit better. And we have an initial condition where we want at time step 0, we want the result to be a sine wave, and the boundary conditions that at x1 and x minus 1, we want it to be 0. And we end up with a loss function that contains the governing equation, 2 boundary conditions, and an initial condition. And when we apply Borrel-Jensen to this problem, this is what we get. So we have here Borrel-Jensen with an exponential decay of 0.999, a temperature parameter of 0.1, and then no lookbacks for now. This is the loss over multiple training runs. So this is the median value. And on the right side, you have the scalings. This is the mean and the variance over multiple training runs. And something that we see immediately is that the scalings have a very low variance. So they follow the training, despite the stochasticity of the initialization, the training follows similar patterns every time. And this is good to see because it allows us to take informed decisions by looking at these scalings. For example, you see that the governing equation was the scaling that had the highest scaling at the end of training once the network converged. And what we can learn from this is that the network might have failed to make further progress because it just failed to model the governing equation better. And what we can do to counter that is, for example, sample more points inside the domain instead of on the boundaries, right? We can to improve the performance of the governing equation, or we could choose some other activation function that has a better shape in the first derivative and so on. That wasn't part of the study, but it's something that's interesting to see that it can give hints as to how we can improve our framework. And then some pedagogical examples on what the effects of the hyperparameters are. In the first row, we still have this high value for alpha, so very smooth scalings, but we vary the temperature. So with a higher temperature, the magnitudes are a bit lower than with lower temperature, and that can can be used to counter or can be used for the aggressiveness of the scaling depending on the problem. And then with alpha, lowering alpha, then of course the stochasticity increases. And finally, if we introduce a random lookback, so the expected value of rho of 0.999 means that we have a lookback at every 1,000 time steps, optimization steps. Then of course it becomes very difficult to learn anything because the variance increases. In terms of performance, we took a manual baseline where we chose or selected the scalings manually, and we compared it to the aforementioned methods. And the first thing to note is that all the methods are viable solutions to get estimate or to choose the scalings, because they are all very close or even better than the manual baseline. So you can save a lot of time by using any one of these techniques, with learning rate annealing and Borrello performing the best here in this case. In terms of median execution times, however, you see that the fact that we don't rely on gradient statistics increases our efficiency, computational efficiency. The second problem is the Kirchhoff plate bending equation. Maybe Michael, you want to take over here quickly? Okay, because he wanted to, Michael?
Yeah, no, so sorry, I did not find the button where to unmute. Okay, so yeah, Kirchhoff plate bending equation, I think is maybe known in the finite element context, because that's usually a hard problem to solve requiring H2 solution spaces. But yeah, quickly to give some background on that. So Kirchhoff plate bending is dealing with thin plates, which can be described by the midplane. And as ever, we would enforce the equilibrium of forces, here marked as this violet dots. That's one equation. The other is the kinematics, so how we would come from the deformations u, v, and w to the inclinations, so first derivatives and the second derivatives, which is the bending and twist curvatures. With linear elastic material law here displayed by the plate stiffness, we can derive the moments, meaning the internal forces. And yeah, as you will see, we would end up with a fourth order differential equation for describing that Kirchhoff plate bending problem. Maybe one note here, because maybe that's not really addressed in the more theoretical papers, but this is very important to the engineering community, be it mechanical or civil. So the W, meaning the deformation of that plate, that would be used to account for what's called serviceability limit state, meaning with that quantity, we would judge if that system performs in a good aesthetic way, ensures durability of the structure, and makes people not feeling unwell. So you can think of if the slab over your head is deforming too much, it may be not a safety problem, but maybe you feel or start feeling uncomfortable. So that zeroth order derivative information, so to say, we would use to do some analysis and judgment. But what is more important, at least for civil engineers, because it's safety related, is the second and third order derivative, because that would be the moments, bending moments, and the shear forces. Because if it is, for example, a concrete slab, we would judge and choose our reinforcement according to that quantities. So I think that's important to know that if you are dealing with that kind of equations, some of the derivatives have physical meaning and they are related to, for example, safety. So investigating the convergence and accuracy of that quantities is really an important thing. Yeah, as I said, so from the derivation, we would see that this is a fourth order differential equation, And now you can have some engineering practical problems, meaning the boundary conditions could be, for example, simply supported edge. So that's the standard in high-rise buildings. This is the slab, which is maybe above your head or below your feet. There is a wall standing along each of the boundaries. So here we would restrict the deformation and the second derivative along these boundary lines. What also can be there is a so-called clamped edge. So that would be your balcony. There is one line supported or more of the lines are supported. We would then restrict the deformations. And for the clamped edges, we would also enforce that the first order derivative has some value. If you think of your balcony, that would be 0 because you want to have your balcony going straight out of your house. What can also happen is the so-called free edge. In the free edge, there would be no support under that respective boundary. And what we can prescribe here is the moments, so the second derivatives, and the third derivatives, which is the loads. Yeah, so far to the engineering and physical background of the Kirchhoff plate bending. And as I said, it's an important problem in mechanical engineering, aerospace engineering, and civil engineering. And therefore, it's nice to investigate that problem. Yeah, Rafael, you want to go on here?
Yeah, thanks. Okay, and what we did was we used an analytical solution. So we used the sine load because the fourth order derivative, of course, we know it. It's again a sine. And that we used to compare it to measure the performance of our network exactly. And in this case, you can see that the governing equation was not the issue, but that the scalings focused more on the boundary conditions here. So the displacements and the moments. Where in this case,
Rafael, can I ask you a question? So this is the strong form, right? In other words, you take A with automatic differentiation, you take the fourth derivatives, right?
Yes, yes.
So no problem there?
No problem there. Fair. Yeah, no problem. You mean for the governing equation, but that's the fourth order derivative. Yeah, it appears so. It appears right. If you look at the scalings, we could say that the network had the easiest time approximating that term, which is surprising. I have to admit that. What can also be noted here is that the moments have the highest scaling at the end of training. But in this case here, since we are in such low numbers here, we could also just say that this might be due to floating point errors. So in this case, this doesn't allow for any conclusions. But still, if that weren't the case, we could again learn something from the scalings here. In terms of performance, this is actually the problem that we first devised Borrel-Jensen for. So it is also the problem that worked best with our method. Here we outperform any other methods and are also considerably more efficient than the competition here. And then finally, the Helmholtz equation, also fairly well known, a second order partial differential equation, which also has an analytical solution. And in this case here, this motivates why we introduced random lookbacks, because if you look at the initial losses here, the governing equation is very high, while the boundary conditions are very low. And what this means is that Borrel-Jensen without lookbacks, it has this initial deterioration here of the of the boundary conditions until the policy begins to react to that, and then it eventually forgets this initial deterioration and ends up with boundary conditions that have a worse performance than they started off with. So this is a suboptimal solution here. Whereas grad norm and learning and rate annealing, they both put a lot of emphasis right from the start on the boundary conditions. So we want to add these lookbacks that remind the network of where it started, and have a very low value of alpha, so the exponential decay, such that the policy can adapt very quickly to this discrepancy here. And the lookbacks help with that. And again, the performances, in this case, grad norm performed best with learning rate annealing and Borrello behinds. Maybe a closer look at the effect of the random lookbacks. Now that we talk of it, you have here the expected value of rho, and 0 means that we essentially always look back to the beginning of training, while 1 means that we don't have any random lookbacks. And a value of 0.9 means that we have an expected lookback every 10 optimization steps. And as you can see, the optimal value for Helmholtz that we found is occurs way earlier than it does for Burgers and Kirchhoff. So this is explained by the problem that I mentioned before, that the initial discrepancy in magnitudes between the terms. And also the optimal hyperparameters, with these 3 ones being the most important ones here, because they're related to Borrello. So the exponential decay rates, they all have rather high values for this exponential decay, with Helmholtz having the lowest one for higher flexibility. And I'd like to remind you that we didn't pick these; that these were picked by Bayesian optimization, so it wasn't biased here, anything. And the temperature. Burgers and Kirchhoff don't need very aggressive scaling, whereas Helmholtz with the 10 to the -5, this is basically an argmax. This turns the softmax into an argmax function here. So very, very aggressive scaling. And the expected saw that. So as I said, not many lookbacks for Burgers and Kirchhoff, and a fair amount of lookbacks for Helmholtz. So as a conclusion, and maybe an outlook as well, we proposed a new policy for balancing physics-informed multi-objective optimizations, which require only 1 backward pass. It enforces the adherence to physics thanks to a weak Pareto optimality, and it matches the state of the art and outperforms it on certain tasks. Looking forward, we would maybe also like to work on incorporating the knowledge of the initialization into this policy, because what we do right now is we assume that a randomly initialized network performs equally bad on all the terms. That's why we look back to the initial loss, right? But this is of course not strictly true, because if you think about boundary conditions that are initialized or that have to go towards 0, and boundary conditions that have to go to any other function, since the network is initialized around 0, of course it will be it will have a lower initial loss for these terms. And since these things are known beforehand, we might be able to have an initialization of this policy which is more intelligent than just taking the initial loss. And another thing that we would like to look into is study these applications of Borrello outside of pins, because of course the loss balancing is, as I said, also something important in other fields. Maybe we could even apply it to balance data sets. If you think about classifications that have many data points in one class and very little in another class, maybe we would like to know if this policy would also work to balance out these tasks. Yeah, so with that, I'd like to conclude our presentation. Maybe, Michael, do you have any additions?
Not to that end. So yeah, as I said before, we thank you for invitation and having the opportunity. Have a look at the paper and let us know, because we would be glad to have some feedback or your experience with that. Yeah, maybe, so we did not put it here, unfortunately. There is a GitHub at Rafael's page where you can also download the code if you want to apply it to your problems. But further from that, yeah, thanks for your attention, and we are looking for the discussion now.
Thank you both. Got 44 people attending on a holiday. That's pretty good. So the I don't think you included the self-adaptive weights, right? From what the guy I call Clever Ulysses from Texas A&M. Do you know that paper by Ulysses Neto Braga?
Yeah, this CFD problem, or is it that?
No. He makes the all the weights trainable, just like as a function of XY time, let's say. And so we had good luck with them. So I was wondering if Shuhui or Sanjay, maybe you can put the paper on the chat for Michael and Rafael. They also have a code that do you see the chat? This is the paper there. Yeah. There is there's also a talk in this seminar from some time ago. Maybe some data could point to it.
Sure, George.
The talk by
the self-adaptive weights talk in June.
Yes.
I could send them the link.
Yes. Then I think you cover all bases. But I have Varun, right? Who some data who did some study between one Paris's dynamic weights and Clever Ulysses. Call him Clever Ulysses. He's from Brazil, but his name is Ulysses, so I cannot resist. But Clever Ulysses, and I think Clever Ulysses wins because it's clever, of course. So Varun, do you have any comments on this for the simple problem you study?
Yes. The self-adaptive seem to be much more easier to work with as compared to the other 2 or 3 methods that I studied. It was just like it did not take too much effort to actually use that method to get to the right solution.
In terms of accuracy, so Varun was doing a boundary layer, a 1D boundary layer, just very easy to, yeah.
And then there's one more method that I think Kai had worked on, that was on the NSF nets, which is very similar to the
one about Paris.
The work from Paris. It just takes the mean value instead of the max that Dr. Michael, you are taking right now for the gradient calculation.
We experimented with both. So we took the median and the mean and the maximum.
Okay. Yeah. So yeah, that NSF nets paper from Kai, that was looking at the mean values, and they found it to be more stable, as far as I understand.
But Varun, you didn't say about the accuracy. What did you find for the accuracy?
Yes. So yes, that's what I said. Like the self-adaptive weight, in order to get to the same accuracy, it took a lot less effort as compared to the other methods, like the method from Paris et al. And other methods. So self-adaptive gave me the best accuracy with the least number of iterations and least amount of effort, I would say, in tuning the hyperparameters.
Yeah, so Rafael, I think it will make a very nice addition to your repertoire of methods in the table.
Definitely, I'll look into that, and I'll try to implement it and compare it. And I'll gladly come back to you with the results. But I didn't, of course, there's just a limited amount of methods that we can compare, right? But this sounds like an interesting thing to do.
I think some data just sent us the GitHub, if I see that right. So we could apply it directly, right?
I think Shuhui has already sent it in the chat, and I will send you the link to the to the talk that we already have.
They actually have they have a extensive code on GitHub.
Yeah. So I have maybe a question to Professor Kaniadakis. So we were a bit thinking about, okay, what PDEs would be cool. So as I said, so I know from finite elements that this Kirchhoff plate bending is a tricky one, posing some problems to the finite element guys. Therefore, we picked that. But I see a lot this Ellen-Kahn equation as well. So
try the KdV and the Kuramoto-Zhivazinski. I think the Kuramoto-Zhivazinski, if you look at the original paper, the KdV, I think we did only the inverse, not the forward. So the forward problems, as you know, pins have difficulty with the forward problems. Not the inverse. They're pretty good in inverse problems, but the Kuramoto-Zhivazinski is like in flames, but it's an instability. And the KdV, some versions of KdV could be depends on how you write them. But I would say either one. And then there's another one that actually Ulysses has in the there's another group, you know, by Chelebi. He's at Stanford. They're doing some work. And they have shown a case that does work, but actually Ulysses in his talk, not in the paper. If you look at the talk, Kraus that he gave, he actually showed also that he almost got it right, but I think you can get it right. So these are, I mean, if you can tackle those, that would be great.
So we talked recently to Gepi because we were a bit interested in, but that is the hyperbolic equation, right? What poses the problems to the pins? What they showed, right? If I remember correctly.
Which one?
I think they had this Beltrami flow.
Beltrami flow. No, Beltrami flow. I think we have it in NSFNet. Not a problem.
Do you remember, Rafael, what this equation was, which caused the problems to the pins?
I'm not sure. Was it called Berkeley-Leverett? Yes. Yes. Yes, that's the one. That's the one. That's the one. And I think in the talk by Clever Ulysses, you will see that he has some results on that. And that's actually what Chelepi from Stanford is using as a counterexample. I think with maybe your method could handle it.
We tried it, but I think what they're trying to do is solving it without the diffusion term, right? And we're not sure if this is feasible at the moment.
Yes, and I think I don't know if Nat Trask is listening today, but he will tell you that you need maybe the entropy condition in that case when it goes to zero. So you need some constraints to do that. Yes. Actually, you're right. That's what also Ulysses is doing. He's sending the term to zero, and then in that limit he cannot get it.
Yeah, so I think that is very valuable hints. So we will definitely look into this KdV equation and use and compare to the trainable weights approach, because I think that makes the paper even better, the methods to be really comparable to what is out there. Very glad that you brought that up. That's nice.
Any other questions for Michael and Rafael?
If we have no more questions, so thank you, Dr. Michael, and thank you, Rafael. It was a very good talk. So thank you.
Thank you a lot.
Thank you. Yeah.
So we move to our second talk. Our second speaker is Nikolas Borrel-Jensen. He would be soon joining the Crunch crew in February, starting in February. So before he begins, let me quickly tell you a little bit about him. So Nikolas Borrel-Jensen holds a master's degree in computer science from the University of Copenhagen, Denmark, and is currently pursuing PhD in virtual acoustics at the Technical University of Denmark. His research focuses on efficient and accurate room acoustic simulations, applying scientific machine learning and domain decomposition methods for spectral element methods and the wave-based methods. Before commencing his PhD, Nikolas has been a software developer and a product owner at the Danish 3D scanner and CAMCAD Unicorn 3Shape, worked with blockchain technology at Eurotalks, and founded the award-winning company LiveTake, improving the audio on smartphone concert recordings. So welcome, Nikolas. You may want to share your screen. And
Nikolas, while you are showing your screen, I just want to say that I spent 3 months in Aalborg shipyard, working in the shipyard, long time ago.
So, Nikolas, you're muted.
So yeah, I'm okay. So you went to Aalborg, you said?
Aalborg, yes. I was supposed to work in the shipyard there, designing a rudder of a big boat, but I was spending my time going between Aalborg and Gothenburg because you could get tax-free drinks on the boat.
Ah, yes.
You know that trick, right?
Yeah, I understand.
This is Scandinavia.
Yeah.
All right, welcome,
yeah.
Mike.
Thank you very much. Yeah, and thank you a lot for inviting me. Yeah, it's a great honor to get the opportunity to present my work. Yeah, so my talk today will be about So I'm a PhD student, as was already mentioned, at the University of the Technical University of Denmark, and I would like to present the work with the title "Physics-Informed Neural Networks for 1D Sound Field Prediction with Parameterized Source and Impedance Boundaries." Yeah, I was already introduced, so I will not say much about myself. So to motivate this work, I would like to show some examples from, for example, from computer games. So I have borrowed these examples from Microsoft Research, from their project Triton. So the first example here is a scene where the acoustics are not taken into account. The next example here is the same, but this time the acoustics is taken into account. So notice how the sound changes when the player moves behind a wall and so on, and the sound attenuates. So these examples shows that taking the acoustics into account for virtual scenes is very important for an immersive experience. So what are the requirements for acoustics in games and mixed reality? So first, from a usability point of view, we would like to automatically calculate the acoustics from predefined scene geometries and boundary materials. So if you are a sound designer in a computer game, typically how it's done today is that you have some trigger boxes and you manually modify the acoustics by defining filters and so on. So by having an automatic system that can calculate the acoustics will help the tedious work. So secondly, we need to handle dynamic scenes, so we can have hundreds of moving sources and receivers. And also, the geometry might change at runtime. So if you open a door or a window, or moves are, walls are moved and so on. At the same time, resources are very limited. So storage should be limited and the computational effort should be small. From a perception point of view, we need realistic acoustics, but we don't necessarily need exact physical reproduction. So what we see here is a sound source emitting some energy, and the illustration here, the animation shows the behavior of the acoustics. So in contrary to, say, light, where you can have shadows, in sound, the waves can bend around corners, as you see here. So you have diffraction effects, and also you have scattering effects when that occurs here at the walls, where the waves are, you can say, they are reflected back in multiple kind of random directions. The way that acoustics is simulated with the current methods is that you have a source, and then you calculate the impulse responses in a grid, like illustrated here. But for dynamic scenes, the source can move around, and so can the receiver. And for each source position, the impulse response needs to be calculated. And that means that, yeah, for every source position, the impulse responses need to be calculated. And this poses some challenges from the storage point of view. So for this example here, if we look at a 2D, you can say slice in a 3D domain of size 20 meters times 20 meters, and we want to simulate up to 4 kilohertz with a duration of 1 second and discretization resolution of 1 meters, we would get 400 points. And if we want to handle the source in each of these positions, that would require us to calculate 16,000 impulse responses, requiring 244 megabytes. Moreover, the computation time can be quite big. So these are some numbers from our in-house DG5 solver running on GPUs. So it's a room of size 9 meters times 3 times 7 meters. And you see that as we go up in frequency, the calculation time grows exponentially. And this is a calculation only for one source position. So imagine if you need to calculate the impulse responses for, if you need to calculate for many source position. So yeah, so this number is only for one source position. So if you need to calculate for many source position, that will be intractable. So we propose a method where we would like to learn a surrogate model, P, that takes 3 inputs. So x0 would be the source position, x would be the receiver position, and then t would be the time. And we would like to model this as a neural network N. So that means that giving some configuration with the source position and the receiver position, then what you will get out from this surrogate model would be the impulse response over time. And the impulse response here is determining you can say the acoustic in the room. So you see what in the beginning here, that would be the direct path from the source to the receiver. Then you would have some early reflections, and then in the tail you will have the late reflections. And having this impulse response, if you convolve that with an anechoic signal, so that means a signal that has been recorded in a condition with no reflections, then you could model how this sound would sound in this given room with the given boundaries, so the given materials on the walls. So first, I would like to show you the underlying equation that we are solving. So we are concerned with the wave equation. So it's a partial differential equation where P is the pressure that we want to determine. X is a coordinate in the domain. T is the time, and C is the speed of sound. And to have a well-posed problem, we also need initial conditions. So for the initial conditions, we are using a Gaussian impulse. And we also need the first derivative with respect to time. So we set the velocity equal to 0.
Nikolas, can I ask you a question?
Yeah.
For the speed of sound, if you have, like in the building that you show us, if they have like columns or concrete and so on, so it's not just the sound has to How do you handle that as a boundary condition, or because it will propagate through or through, let's say, through a wall that goes to the next wall? That will be a heterogeneous.
Okay.
So it's it will be a variable. It will not be a constant C, right?
Yeah. So I mean that if you
heterogeneous medium. Yeah. If it was a heterogeneous medium. Yeah.
Yeah. So transmission through a material to the other side.
Yeah.
Or
yeah.
So we are not modeling. We're only modeling reflections for inside a domain in this work.
Okay.
Yeah. Yeah. So, and we also need some boundary conditions, and we can have different boundary conditions like Dirichlet boundary condition, Neumann boundary conditions, but because we are concerned with room acoustics, we would like to model the boundary conditions as frequency independent and frequency dependent boundaries. So I will start with the simplest first. So frequency independent boundary condition. So the surface impedance is telling us how much material is absorbing the energy, and it's given by this equation here, where C is the surface impedance, P is the pressure, and V is the velocity, the normal velocity at the boundary. And this is so the ratio between pressure and velocity is determining the surface impedance. The wave equation I showed on the previous slide is determined only with respect to pressure, but actually you can describe the wave equation as a two-coupled equation given by pressure and velocity. And we will exploit this to model the boundary conditions. So we will combine the surface impedance here in 1 with the pressure term here in equation 2, which will give us the frequency independent boundary formulation that we will apply at the boundary. So this would be our boundary condition, where psi here is the normalized acoustic impedance. For frequency dependent boundaries, it's a bit more involved. So in reality, you would have some kind of absorbing material on the wall, and most material don't absorb equally in the frequency band. So let's say for higher frequency, maybe some material will absorb more than lower frequency. And you will have some phase shift and so on. And yeah, so we can rewrite the impedance here as the admittance Y, and this can be written as a rational function which we see here. This one can be rewritten using partial fraction decomposition, and then we get a formulation like this, where Q here is the number of real poles that we want to include in our fitting, and S is the number of complicated pairs. The other parameters here is determined by some method that is kind of modeling the material that we are concerned about. And notice here, this formulation here is in the frequency domain. And since the wave equation is described in the time domain, we need to use the inverse Fourier transformation to the admittance and the partial fraction decomposition term. And combining these, we get this formulation here in the time domain. And notice that we have introduced now two new terms, phase and size. And these can be determined by a coupled system of equation as ordinary differential equations given by these terms here. So we need to solve these equations to get the phase and size, which are called accumulators. And when we have these, we can insert them in this formulation here and get the velocity term. The velocity term now can be inserted into the pressure term from the coupled equation from the wave equation, which gives us this formulation here at the boundaries that we need to solve. So these are you can say the underlying physics, the underlying equations that we want to solve. And of course, these can be solved using various methods, like traditional numerical methods, like spectral element methods. But in this work, we have focused on using pins. So I will not go so much into into pins, of course. Just saying that the network architecture that we have been using in this work is a feed-forward neural network with input layers and hidden layers. And yeah, the objective is to determine the weights and the biases through a minimization problem where we want to minimize some observed values minus the residual of the error. Yeah, and these weights are determined by the backpropagation algorithm by applying the chain rule, and a key ingredients is, of course, the automatic differentiation included in most modern frameworks like TensorFlow and PyTorch. So the setup for this case here, we have created, we are using two neural networks, one for predicting the pressure and a second network. So this is for frequency dependent boundaries. One for predicting the pressure and another one for predicting the accumulators. And we have parameterized the source position x0, and then we have the time and the spatial coordinate here x. So it's you can say it's a spatial 1D problem, but yeah, we have three parameters for our problem, or for yeah. And the ADEs here are included in the loss function, or the residual is minimized through the loss function. And having determined these, the output from this neural network, the accumulators, we insert them into this formula, this equation that I showed before. We get the velocity out, and we use the velocity in the governing equation for the boundary condition, and apply these at the boundary and predict the pressure value P. So the loss function that we want to minimize consists of 4 parts: the loss for the PDE, the loss for the initial condition, the loss for the boundary condition, and the loss for the ADEs. Where the loss for the PDE is simply the wave equation, and the loss for the initial condition here is the residual, and H here is the Gaussian that I showed in the previous slide, and the velocity term, and the boundary conditions here. Note here, yeah, now Rafael did a very great talk about the penalty weights that is typically needed to make the network perform well. So yeah, we're also using these penalty weights here to weight the different terms. The velocity here is giving through the loss function for the ADEs that I will show on the next slide here. We have this loss term here, and the different losses are given by these ordinary differential equations, the auxiliary differential equations. And again, we have introduced penalty weights for the different loss terms in the for calculated the ADEs. Note also that we have added another term here inside inside the loss function, and this has been introduced in order to make the output from the accumulators take values between 0, 1, and 1. And this was needed to make the network perform well. The activation functions for this network here, we have used the hyperbolic tangent function, and that naturally gives values between -1 and 1, and that's why we have normalized the output from this network to take values in that range. I will say a few words about the sign activation function, because the sign we have used the sign activation functions for the main network predicting the pressure parts, and using the sign activation function instead of, for example, the hyperbolic tangent function showed that the convergence happened much faster. So it was a huge gain to change the activation function from to a sign exchange function. And this has been described in these two papers. I don't know if you're aware of these, but it's I think it's not so often used in deep neural networks.
Nikolas, actually, in the paper, in the Marja Raisi, who is the author of the PINS paper, in his paper in Science, he's using for the fluid mechanics, he's using sign activation functions. So he introduced them in a Science paper, but I know that was his favorite. He didn't.
Okay.
He didn't write a separate paper for it, but
Okay.
he was using them quietly. I mean, it's in the paper. You will see there, the Science paper 2019.
2019. Okay.
Yeah.
Okay. Yeah. So one of the reasons that the sign activation function might be a better choice is that we can have higher order derivative of the sign. And moreover, in the second paper here, they have shown that to some degree, using the sign activation function is similar to representing the solution as a Fourier series. So that could be some of the reason that we see better convergence using this sign function. And one thing that is crucial is to initialize the weights when the sign functions are used so that they preserve the distribution of activation across layers. So in the first paper, if you assume that the input is uniformly distributed in the range -1 to 1, then we draw some weights uniformly in this range here with omega 0, which is a parameter that can be tweaked. So that depends on the content of the frequencies, how this one should be chosen. But the paper suggests to use a value of 30, and that's also what I have been using, and it seems to perform quite good. Yeah, I would like to show some experiments. So I would like to show results for frequency-independent impedance boundaries and frequency-dependent boundaries, and also a few words on runtime efficiency. So the domain size is a 2-meter domain from -1 to 1. The simulation time has been chosen up to 0.012 seconds. So that means that we will have 2 reflections. So in this case here, we will have initial condition, that's our Gaussian, and then the wave will start traveling. It will reflect back from the boundary, which will have either frequency independent or frequency dependent boundaries, and it will travel back. So it will have 2 reflections back and forth and end at the initial position. We simulate up to 1,000 Hertz, and we use the Gaussian impulse spanning frequency up to 1,000 because that is that is the range we want to simulate. The data has been distributed so that the source position is uniformly distributed at these positions. So that's what you see down here. And for evaluating the results, we have compared the impulse response at these positions here. But I will come back to that on the next slide. The reference solution has been calculated using a spectral error method, but I think 20 points per wavelength, so that we have a very good reference solution. So the parameters for the network, we have used 3 layers for both of the neural networks, and 256 neurons for the network predicting the pressures, and 20 neurons for predicting the accumulators. We have used, as I mentioned, the sign function as activation function for the topmost neural network, and the hyperbolic tangent function for predicting the accumulators. And using ADAM optimizer and the mean square error loss function. The number of, so the number of total points used is around 47,000 points, and the points has been distributed with 45% of the points at the boundary condition here and here. So here we have x is the spatial dimension here, and t is in this dimension here. And we have chosen to, we've used 45% of the points at the boundaries and 25% of the point at the initial condition. And then the last 30% of the points in the inner domain here. So that means that we have around less than 7,000 points per source position, giving us 7.6 points per wavelength. The weights has been set with a weight of 20 for the initial condition, and the weight set to 10 for the lambdas, for the penalty weights for the auxiliary differential equation. So it was very crucial actually to put a very high weight for the initial condition, and also distribute quite a lot of the points at the initial condition. So here we see, I will show you an animation over time for the result here. So the top row here is the pressure in the spatial domain. So we initially, so this is, and the columns here are the source position. So we have source position minus 0.3 minus 0.15. So this is, so we are evaluating this one in a position that has not been trained. So in interpolation between 0.3 and 0, and the same for this position here. In the second row here, that is the pressure at the receiver point. So the dotted line here is indicating where we are. So that actually corresponds, if you want to think about a room, you have some kind of source, and then you have a microphone somewhere else. So that you can say that the microphone in this location here is recording the sound pressure or the wave traveling in this domain. So in the second row here, we see the pressure at the receiver positions indicated by the dotted line here. And the last row is the error over time. So you see here that the wave now starts traveling in two directions. The wave hits the receiver position, which we also see from the second row here. And the blue line is the predicted pressure from our network, and the red dotted line is the reference. So we see that the predicted and the reference is fitting very well, and we have very low errors down here. The next example here is the same, but for frequency dependent impedance boundaries. So maybe I should say a bit about how the parameters were fitted. So we have used a model called Mickey's model, where you determine. So it's a model that models porous material. So so the D here is the thickness of the material, and rho is or sigma here is the flow resistivity. So it's telling something about how much resistance the material has. And from these parameters, the parameters for our frequency independent coefficients are determined. And again, we see the traveling wave. We see that the wave is reflected and it's attenuated. and travels back. And again, we see that the predicted and the reference solution fits very well again. Yeah, and just a few words. So this illustration here is showing us how well the accumulators are being predicted. So in the bottom part here, it's just for a single source position, and the accumulators, the values of the accumulators here are being plotted over time. And again, the blue line is the predicted, and the red line is the reference solution. And yeah, we again see that the prediction and the reference, that the prediction is very good. So some numbers. So I have calculated the relative error in the receiver position. So that means that, as I explained before, so that's where you have your microphone recording. So that's the values that are compared, and we see that we have relative errors below 2% for all of the source positions, both for frequency independent and frequency dependent boundaries, which corresponds to around 0.2 decibel. And as a rule of thumb, you can say that if you have errors below 5–10%, then it can be considered that it can be considered that there will be no audible differences between the signal. So just a few words about the runtime efficiency. So as I explained in the requirements, when you to make this useful in virtual environments, we need to be able to execute the model very quick at runtime. So this example here, or this experiment, is evaluating how efficient we can evaluate our surrogate model at runtime. So we are simulating, or we are predicting for half a second at sampling frequency 44 kilohertz with two source position and a receiver position, which gives us an impulse response of 22,000 samples for our impulse response. And for this example here, we had an execution time of 64 milliseconds, which is considered real time. But of course, this is for this very 1D, very simple model. So to really validate whether we can reach real-time execution, we need a more realistic scenario. So in summary, we have used PINs to build surrogate models for retrieving impulse responses in grid-less domain. We get very good results below 2% for frequency independent and dependent boundaries with moving sources. We get real-time execution. And of course, there's a lot of things to do for the future. We see quite slow convergence, up to 3 orders of magnitude slower than to train than traditional methods. And yeah, we have also seen that it can be difficult for the optimizer to achieve good results when the domain gets bigger or we increase the frequency. I have a few slides where I will go a bit more in details, where I hope we can also discuss what we can do about that for the future. And of course, the aim would be to go to complex 3D scenes. So yeah, I would like to continue a bit, and I would like to open up the discussions now. That if you have some comments or some suggestions for how to overcome these challenges, please interrupt me. So I mentioned that if we increase the domain size, or we will narrow the pulse of the width, then I saw some problems, converging to low errors. So this is an example, like making the domain twice as big or narrowing the pulse, which is basically the same, you can say, problem. And of course, one solution could be to use XPens, like splitting the domain in 2 parts and then solve the domain individually. So I think that could overcome some of the challenges, and hopefully we could also reuse the parameters estimated in the different, you can say, if you have estimated the parameters for this domain and you want to make the domain bigger, then you can hopefully keep the parameters, the weights for the loss function in the different parts. So slow convergence, one thing that could maybe improve the convergence could be to take time dependent into account, like using ResNet or recurrent neural networks. And I don't know if any of you have had any experience with that. So basically ResNet is an architecture where you kind of use some skip connections, and you can see there has been some papers comparing these architectures with Euler steps or Runge-Kutta steps. So that this is a way to, you can say, model time dependence. Yeah, other ways could be to use convolutional networks or DeepONet. Yeah, I don't know if yeah. So at least some ideas for improving the convergence. Lastly, and some challenges of the parameter estimation. So estimating the weights can be quite tedious and not that easy to determine, and it's very, you know, taking a lot of time and not very interesting work. So I was very happy to see Rafael's talk, and I will consider applying some of the methods to determining the weights for the different loss terms. Also, some proposal has been to construct an ansatz where you actually don't need to divide your, let's say, your boundary initial conditions in several loss terms, but where you construct one loss term and you optimize on that. An interesting paper here about that. And also the grid point distribution, like I distributed with 24% of the points at the initial condition and 45% at the boundaries, and all. I mean, all these parameters, you need to tweak them, and they are, you can see they depend on each other. So it's quite tedious to find the right parameters.
Nikolas, we had the first, this paper, we had those two giving a joint presentation to Crunch. It's one of the recordings. You will find them.
Okay.
And Suku will be here. He wants to spend a sabbatical here. Yeah.
Okay. Another interesting, I would say, yeah, some interesting work would be if we could kind of make some more theoretical, you can say, more theoretical could determine the degrees of freedom in the neural networks with regard to number of layers and neurons, depending on, let's say, the frequency content of the problem. And maybe that could be by connecting it to the theory to Fourier series analysis. Maybe some theory could be created to beforehand determine how many layers and neurons we need to get good results for a given problem. Because I guess this is something that is missing a bit in compared to traditional numerical methods. I think that was all for me. Thank you very much for listening, and yeah, feel free to ask questions.
Thank you.
Thank you, Nikolas.
Can I make a suggestion, since you, Lulu is not here, but he worked with ANSYS on a similar problem, where basically they were looking at power electronics, and they had like a source, and they moved around the source, and they want to see how the heat distributes in a electronics box. And so you can use DeepONet to do that in advance. So you amortize the cost all in offline training, and then and that was for 2D and 3D problems. So no matter what, if it's 2D or 3D, then you can actually predict in real time. He had like on a laptop, you can do 0.01 seconds. You predict in 0.01 second, no matter what.
Okay.
With DeepONet. So DeepONet eventually, for this problem, Nikolas, DeepONet is the way to go. Of course, there are lots of things, or physics-informed DeepONet, where you can actually have the loss like you have. So you're not gonna miss out anything. Some data was doing like this hybrid where she had a few runs and then a lot, and then the physics together to train a DeepONet to do crack propagation, for example, which is also a difficult problem. But I think with DeepONet, for this, you can actually, DeepONet, I'll be interested to recreate those images that you show us in the beginning, but I don't like the killing too much. But the rest, the sounds I was fine. So we have to find another problem.
Yeah, but
I'm against blood, so I don't like this type of war games. But we'll find some other 3D thing with sound effects.
Yeah, sure.
But DeepONet would work. I think ANSYS invested on this exactly in that, and they wanted real time. Yeah.
Okay.
Yeah.
Okay. That sounds interesting. Yeah.
Yeah, Raj, I don't know if Raj is on there, but Raj has been working with ultrasound and non-destructive evaluation of materials for wave propagation. So he had the speed of sound, he had it as a separate neural network. So he got really good results on that. He's published his paper.
Okay.
So Raj is the guy who did the parallel pins also.
Okay.
So, Nikolas, I had just one couple of questions.
There is Raj.
Okay.
So in one of the slides, you showed that there is an attenuation. So it's kind of viscoacoustic effect. And that case, your speed will be dependent on the frequency. But in equation, you did not consider that, like how it is learning then.
So I talk about these animations here?
Yeah. In one of that, you showed the attenuation there. Yeah, what is this sigma mat physics, this one?
Yeah, so this is the flow resistivity. So you can say the material is modeled through this. You can say the impedance that I showed in one of the slides, and this was reformulated with a rational function that was again reformulated in the time domain. And these different coefficients, they are determining, in this case, a porous material. So these two numbers here, this is the flow resistivity is determining the type of material. So how difficult it is for the pressure or the sound to enter or travel through the material, right? And this is the depth of the material or the thickness of the material.
So, but wouldn't be the frequency dependent, this sigma mat physics, that?
No, so this is just, so the frequency dependence is given by, let me find it. So you see here, so this is some, you can say some complex function that is determining the velocity of the material, right, at the boundary. And the velocity here is dependent on, is frequency dependent.
Yeah, that's my question, because so. Okay.
But the material here, the speed of sound, or you can say the material is homogeneous. I mean, the material is of course has the same properties everywhere, of course. But
okay.
So what do?
Yeah. Okay. And why you need the frequency dependent boundary condition? Why not just simple vanilla absorbing boundary conditions?
So you can say, I mean, in real life, materials are not that simple. So if you want to get closer to reality, then you need frequency dependent boundaries. You can of course discuss whether it's needed for computer games. So that's another discussion, yeah. But I mean, in our group, we're also concerned about modeling sound for architectural design. So let's say you want to build buildings, right? You want to be able to listen to the acoustics before building. So in that case, it's important to actually reproduce the physical world as precise as possible.
Okay.
But it's a good point. It's a good point whether it's needed for virtual environments.
Yeah, because I work for materials and bones, and we just simply used that absorbing boundary conditions and like simple, sometimes PML, but that works very well. So I'm not sure like how it will affect the simulation, but yeah.
But I think it is very important if you want to model the real world precisely, then you need frequency dependent boundaries.
Okay. Thanks, Nikolas. Thank you.
Yeah,
okay, that's a good introduction, Nikolas, because Raj, you will be working with Raj when you you come here. So that's a good introduction.
Sounds good.
Thank you.
Are there more questions for the speaker? If you don't have any more questions, we could actually call it a day, and some of us can go back to shopping if they want to, because it's Black Friday. So yeah, wish you, thank you, Nikolas, thank you, Michael, thank you, Rafael. The presentations were really good, and I will send you the links of the recordings so that you could have a look at it. So thank you.